Supercomputing on a Phone, copyright MIT, February 11, 2010, by Phil He, David Knezovich, and Tony Patera, with contributions from many colleagues. We consider transient heat conduction in a cube consisting of 8 subcubes of different conductivities. The conductivity of the first subcube is set to unity. The normalized conductivities of the remaining 7 subcubes can be chosen between 0.5 and 2.0. In this first instance, the conductivities are all unity except the second subcube, which has a conductivity of 0.5. We set the reduced basis dimension to 10 and solve. Initially, the temperature is 0. A flux is then applied at the bottom boundary. The 4 outputs correspond to the average temperature as a function of time in small subdomains near the 4 corners of the heated surface. We focus on the second output, which measures the temperature in the second, in this case low conductivity, subcube. The second output is represented in the plot by the red lines. The dark red line is the inexpensive reduced basis output prediction computed online by the phone. The 2 light red lines are the inexpensive reduced basis output bounds, also predicted online by the phone. It can be proven that these 2 light red lines rigorously bound the output prediction we would have obtained had we performed a supercomputer calculation, an expensive, very high resolution, highly accurate simulation on a proper machine. Our reduced basis error, the gap between the light red lines, is clearly too large. We now increase the reduced basis dimension to 45 and solve again. We must now wait slightly longer for the phone to compute the reduced basis result. We see that the gap between the dark red line and the 2 light red lines is now deemed acceptably small. Hence, supercomputing on a phone, more precisely the equivalent of supercomputing on a phone. We may now visualize the result. We present results for the temperature as a function of time on the cube's surface. Lower conductivity regions, such as the second subcube, result in higher temperatures, represented here by the red isotherms. We may now change the parameters. The reference conductivity in the first subcube remains unity. We set the conductivity in the second subcube to 2.0, and the conductivity in the 6 remaining subcubes to 0.5. We again solve, but now for these new values of the 7 parameters. We may vary the parameters in real time, here on the phone, but more generally in embedded and deployed contexts. Limitations apply. Offline costs for the development of new datasets can be considerable. This application is not appropriate for small children or other individuals inexperienced with partial differential equations.